So today we're going to learn stoichiometry, and for this we're going to look back at other things we've already done with our conversions. So you always can convert one thing to another if you have a conversion factor. So for stoichiometry, the conversion factors are going to be molar mass, when we need to go between grams and moles, if we needed to go between atoms and moles or molecules and moles, we would use Avogadro's number. But most commonly, we're going to use molar mass to go between grams and moles, and then we're going to use something called a mole ratio. So a mole ratio is when we compare substances from the balanced equation, okay? And it's just the coefficients are the moles. So in this equation of N2 plus 3H2 goes to 2NH3, we could look at that as one molecule of N2 reacting with 3 molecules of H2 to make 2 molecules of NH3, but we're never going to really be reacting only 1 molecule and 3 molecules. So more commonly, we think of those as mole amounts, mole ratios. 1 mole of N2 can react with 3 moles of H2 to give us 2 moles of NH3. Okay, so those are our mole amounts, and they are crucial to any stoichiometry problem. Stoichiometry just means quantity. It's a Greek word for calculating quantities. So we're going to be doing lots and lots of stoichiometry, calculating quantities from our balanced equations. So on this paper, it says, write the 6 different mole ratios. So looking to this balanced equation, we could say, well, there's 1 mole of N2, and our abbreviation for mole can just be, excuse me, MOL. We can just drop off the E. So in the equation, there's 1 mole of N2 to 3 moles of H2, right from the balanced equation, right from those amounts given here. Just looking at the coefficients, okay? So understood that it's just a 1 if there's no number in front. We could flip that. We could say there's 3 moles of H2 for 1 mole of N2. Or we can compare our N2 to our product. We could say there's 1 mole of N2 to 2 moles of NH3. Again, just looking at the coefficients, those are our moles amounts. We could flip that one. 2 moles of NH3 is equal to 1 mole of N2. So we've compared one reactant to the other reactant. We've compared one of the reactants to the product. And then now we can compare the other reactant to the product. We could say there's 3 moles of H2 to 2 moles of NH3, or we could flip that. 2 moles of NH3 is equal to 3 moles of H2. So those are our 6 possible mole ratios, right? For this particular equation, they're only good for this equation. So now we can look at that balanced equation, and we can use those mole ratios to answer questions. So how many moles of NH3 are produced from 1 mole of N2? Well, for that one, we can just look to the equation. There's 1 mole of N2, and how many moles of NH3? 2. So our answer is 2 moles. We didn't have to do any calculations because that exactly matched our equation. But when we have a little bit different numbers plugged in there, now the second one, sorry, it's just leaking out a little. How many moles of H2 are needed to react with 2 moles of N2? Okay, so for 2 moles of N2, and then in the equation, we see the ratio is there's 1 mole of N2 to 3 moles of H2. So there is, why is this going crazy here? Come on. I'll do it on here. For 2 moles of N2, okay, 1 mole of N2 gives us 3 moles of H2 according to the balanced equation. So we would need to react 6 moles of H2. Okay, a mole to mole ratio. So we're starting in moles of N2, so N2 has to go on the bottom. The number of moles of N2 is from the balanced equation. So this is called our mole to mole ratio. And then we want to go to H2. So we look to the balanced equation, and there's 3 moles of H2 in the balanced equation. Okay, doing another one. How many moles of NH3 are produced from 5.4 moles of N2? So there's 5.4 moles of N2. We need to go from moles of N2 to moles of NH3. And in the balanced equation, there's 1 mole of N2 to 2 moles of NH3. So now we are out of N2, we're in moles of NH3, we just multiply. 2 times 5.4 is 10.8 moles of NH3. Okay, so for this balanced equation, these mole ratios are conversion factors, just like we had all the other conversion factors, inches to centimeters and kilometers versus miles and all that. These conversion factors for this particular equation are those mole ratios that we get from the balanced equation. All right, let's look at another one. 2 moles of carbon plus 1 mole of oxygen gives 2 moles of CO. So just like before, we can go from moles of oxygen to moles of carbon monoxide based on our balanced equation. Okay, how many moles of carbon monoxide is what we're solving for. Mole to mole ratio we get right from the balanced equation. We're in moles of oxygen, and it tells us there's 1 mole of oxygen to 2 moles of carbon monoxide. Our mole to mole ratio from the balanced equation. If we want to add in grams, then we use molar mass again, just like we've been doing to convert between moles and grams, we use molar mass. So the first one, we're just going to do mole to mole again, and then we can add in grams. So for this one, we have 2.23 moles of oxygen, and in our balanced equation, there is 1 mole of oxygen to 2 moles of carbon monoxide. So 2.23 times 2 is 4.46 moles of carbon monoxide. But then the next one adds in grams, and it says how many grams of CO are produced. Okay, so now we add in molar mass. So from 2.23 moles of oxygen, which I just did above, okay, I went to moles of, that kind of looks like CO2 because let me fix that. So I can combine that. Okay, we went from moles of oxygen to 2 moles of carbon monoxide. Okay, that gets us out of moles of oxygen. Now to go to grams of carbon monoxide, we need molar mass. So 1 mole of carbon monoxide, so oxygen weighs 16, carbon weighs 12. So the molar mass of carbon monoxide is 28 grams per mole. So 28 grams is the molar mass of 1 mole of carbon monoxide. So now on this one, we'll have the 2.23 moles. We converted that to moles of carbon monoxide, which again, up above we did, it was 4.46. Now to go on to grams, we need to multiply by the molar mass of carbon monoxide. So, and we get 124.9 grams of carbon monoxide. All right, so starting in moles, you always will do your mole to mole ratio. If you want to go on to grams, then you use molar mass. Okay, let's try a couple more. How many grams of carbon are needed to react with 2 moles of oxygen? So I have 2 moles of oxygen. I want to go to carbon. According to the mole to mole ratio, there's 1 mole of oxygen in the balanced equation to 2 moles of carbon. Okay, that gets rid of moles of oxygen. Now, 1 mole of carbon weighs 12 grams. That's the molar mass. So from moles of oxygen, we get to moles of carbon with the mole ratio. Then we use molar mass to get to grams of carbon. So that will give us 4 times 12. That will give us 48 grams of carbon. Okay. And then how many grams of carbon are produced when 4.83 moles of carbon react? How many grams of carbon monoxide are produced when 4.83 moles of carbon reacts? So 4.83 moles of carbon from our balanced equation. Looking back up at our balanced equation, the relationship between moles of carbon and moles of CO2 is 2 to 2. So there's 2 moles of carbon to 2 moles of CO. I think I just said CO2. CO. And then I want to go to grams of CO. So 1 mole of CO. And again, the molar mass. This is molar mass. To get to grams, 1 carbon is 12. 1 oxygen is 16, so the molar mass is 28 grams. Now it's 4.83 times 2 divided by 2. Those 2 cancel out. Okay, moles of carbon, moles of that. So times 28. And that equals 135.24 grams of carbon monoxide.